Hello class. So in this video, we're still on section 3.2/4.1. It's a long section because we have to introduce all this notation terminology from linear algebra, but we're getting to the point where it's gonna pay off because if you remember in the previous video, I defined what a Wronskian is, right? And I showed you examples of how to compute it. Now we can relate the Wronskian to how to tell whether a set of functions are linearly dependent or independent on a given interval. So that's the theorem. So let y1, y2, all the way up to yn be n solutions of an nth order linear ODE. So here I write nth order linear ODE on some interval I, because for our purposes, our functions are always going to be solutions, right? Those are the things that we're looking at and we're interested. I haven't told you why, or we're interested in whether they're linearly independent specifically. But in general, you can replace, so these don't have to be solutions. You can replace them just by functions, right? This should just be any functions in general. But again, we're focusing on solutions of linear ODEs, right? So reading it more generally, let y1, y2 up to y sub n be n functions, right, on an interval I. So then the set of solutions or functions is linearly independent on this interval I if and only if the Wronskian of these functions is not equal to 0 for all x in I. And that's it. Given a set of functions, how are you in, and notice that in the case that these functions are solutions to linear ODEs, which is going to be our purpose, this I, this interval, is usually going to be the shared interval of definition, right? So interval of definition that works for all of them. So let me write that note. I will usually be, for us, usually be an interval of definition that works for all of them, for all the solutions. Now, of course, as I mentioned in the previous video, there are other things that could restrict I, like the domain of the functions, but that's already included in the interval of definition, right? Remember when we talked about the interval of definition, the functions have to be defined under interval of definition. So that's kind of taken care of. This could still affect our interval, right? Because we could have solutions, but what if they're not n minus 1 times differentiable? Well, if you assume that there are solutions to an nth order ODE, they're at least n times differentiable, right? Because you have to take their derivative n times. So that won't be a problem for us. So really, in the case that we're working with solutions of an nth order ODE, I is really almost always, I can't think of something right now where it won't be, but it's always going to be, or almost always going to be the interval of definition that works for all functions, right? All solutions. In the general case, again, I is going to be restricted by these three things. Right? So if we want to check if our functions, specifically solutions of an nth order ODE, if we want to check whether they're linearly independent on their interval of definition, just calculate the Wronskian. If it's not equal to 0 for every x in that interval, then they're linearly independent. If it is equal to 0 for some x on that interval, you're going to have to make your interval smaller. But that's it. This is an algorithmic way to compute this because I've given you an algorithm, at least for the 2 by 2 case, and for the n by n case. So when you have n functions, and your matrix is going to be an n by n matrix, how do you compute the determinant of that? Well, I'm going to show you how to do it in Mathematica. Right? So I already showed you how to do it in the case that you have two functions. So now you have an easy way to tell whether your functions are linearly independent or not. So again, I told you this is going to be an amazing theorem, definitely way better than the analysis we did before. Okay? Let's jump right into an example. Right? We already showed the definition way that x and x squared are linearly independent for all values of x. Now let's use the Wronskian. Okay? Right. So let's calculate the Wronskian of x and x squared. Right? Notice that these are functions, right? They're not necessarily solutions. So we don't really have to worry about an interval of definition in terms of on what intervals to satisfy a differential equation. All we have to worry about is, well, there are two functions. They need to be at least one times differentiable, which they are, right? Derivative of x is 1, derivative of x squared is 2x, so those exist everywhere. So we can calculate the Wronskian, and they're defined everywhere. So we can calculate the Wronskian on the whole interval I equals negative infinity to infinity. Okay? So by definition, this Wronskian is going to be the determinant, or yeah, this determinant. So first column is your function, and then its first derivative. Second column is your second function, and its second derivative. And again, it doesn't matter in which order you put them in, as long as the columns match. So you can put x squared in the first column, but then the entry below it has to be the derivative of x squared. So it's going to be, so x times 2x, so that's 2x squared. So yeah, so 2x squared. And then minus, so now we do the other product, x squared, right? Which equals 2x squared minus x squared. This is x squared. Now, these functions are going to be linearly independent on an interval as long as this Wronskian is not equal to 0. So in this sense, this is a little bit weaker than the actual definition, right? Because we already know that these functions are linearly dependent everywhere, right? On negative infinity to infinity. However, remember by the past theorem, how do we find on what intervals are these functions linearly independent? Well, we set the Wronskian equal to 0, right? And we find the largest interval on which, you know, this Wronskian is not equal to 0. So the fact that this Wronskian equals 0, right, means that in terms of the Wronskian, we would either have to choose the interval negative infinity to 0 or 0 to infinity, because we don't want to include this place where the Wronskian is 0. So here you can see how this tool is a little bit less powerful, which kind of makes sense because it's not the exact definition. However, for most purposes, this is going to be enough. So let's say if this represented time, we would probably choose this interval. So x and x squared are linearly independent on both, right? You usually choose one to work with, but they're linearly dependent on both of these intervals. Again, we know that they're linearly independent everywhere. However, we don't get that from the Wronskian. But again, this is usually enough. The interval you get from the Wronskian is usually more than enough. It's usually what you need. Okay. And again, we bypass all this complication of having to use the formal definition of linear independence. Okay. So another example. Determine whether y1 equals e to the 3x, and we should have written y2 equals e to the negative 3x are linearly independent on I equals negative infinity to infinity. So we need to show that the Wronskian is not equal to 0 on this interval. Okay? Just calculate the Wronskian. Now notice that both of these functions are not only one-time differentiable, but infinitely many times differentiable and defined everywhere. So we can calculate this easily. This is e to the 3x, its derivative, e to the negative 3x, and its derivative. Oh, forgot the 3. So that's what we need to compute. So let's go ahead and do it. So multiply the first diagonal entries, right? So we get e to the 3x times e to the negative 3x. Sorry. times negative 3 e to the negative 3x minus the product of the other diagonal entries, right? So minus e to the negative, let me keep the same color, minus e to the negative 3x times 3 to the e to the 3x. So just multiply the diagonal entries and subtract them. Let's simplify. We get, remember that multiplying exponents with multiplying exponents with the same base, you just add them, right? So multiplying same base, sorry, you add the exponents. So e to the 3x plus or times e to the negative 3x is the same as e to the 3x minus 3x minus, same here, 3 e to the negative 3x plus 3x. Oh, sorry, I forgot a minus in front of this one. Yeah, so there, I put it here on the first one, but I didn't write it before. So we have negative 3 e to the 3x minus 3x minus 3 e to the negative 3x plus 3x. Okay, so I did that right. So what do we get? E to the 0 minus 3 times e to the 0. Any number to 0 other than 0 itself is 1. Negative 3 minus 3, which equals negative 6. So the Wronskian of these two functions is negative 6, which of course is not equal to 0 anywhere because it's a constant, which is non-zero everywhere, which implies these functions are linearly independent everywhere. So everywhere is the same as saying from negative infinity to infinity. Simple, right? Very simple. Again, in some cases, so in the previous example, you lose a little bit of information. Right? So you lose 0 from your intervals. However, as I said, most of the time, losing 1 point or a couple points is fine. Usually the intervals that you do get are more than enough and are the ones that you're interested in. If not, then you have to use another method. But for this class, this should be enough, right? And then of course, sometimes you just get everything. So that's good. So this is how to find whether functions are linearly independent on some interval. And again, this is going to be important for what we're doing next.